Hello, my name is Mikhail Bragin, and the title of my today's presentation is Surrogate Level-Based Lagrangian Relaxation for Mixed Integer Linear Programming. Mixed integer programming is pervasive in many fields. It plays an important role for the problems of importance to society. For example, MIP problems are prevalent in smart manufacturing, traditional smart grids, logistics and transportation, chiller plant optimization, healthcare, building evacuation, AI and machine learning, and cybersecurity. In today's talk, I will focus on separable mixed integer linear programming problems. Such problems are viewed as I subsystems which are coupled together. Accordingly, the objective function is to minimize the summation of individual subsystems objective functions. The minimization is subject to coupling constraints which couple individual subsystems. The goal for those problems is that they need to be solved fast. For example, within power systems and manufacturing, they need to be solved within 20-30 minutes. Within healthcare, within 5 minutes. Within building evacuation, within even 5 seconds. So what are the difficulties of those problems? The difficulties are the presence of integer variables. They lead to combinatorial complexity. The complexity grows exponentially as the problem size increases. The second difficulty also comes from the presence of integer variables. Because of those, there are no derivatives and no necessary conditions. If the problem were purely continuous, one could take derivatives to find the optimal solution. When some of the variables are integers, that is not possible. So what is the goal for practical MILP problems? Can those problems be solved optimally? Because of the combinatorial complexity, as mentioned before, this goal cannot be achieved. Instead, the goal is to find near optimal solution with quantifiable quality, for example, with a gap less than 1%, in a computationally efficient manner, I'll say within 20 minutes, 5 minutes, 5 seconds, depending on the problem. In this talk, I will present the novel Surrogate Level-Based Lagrangian Relaxation for Separable MILP Problems. I will exploit separability, linearity, and duality. At the end of the talk, I will provide a note on generalization of the results to solve also nonlinear problems. The gist of Lagrangian relaxation is to relax the coupling constraints. For separable problems, the relaxed problem can be decomposed into individual subproblems associated with individual subsystems. And then the dual function is maximized. The advantages are, because of the decomposition, complexity is much reduced. The size of each subproblem is much smaller, therefore complexity decreases exponentially. Another advantage is that the dual problem is continuous and convex. But what are the pitfalls of this method? The first difficulty is that when the number of subsystems is large, the computational effort can still be high. Second, while dual function is continuous, it's non-smooth, which means that the gradients do not exist along the ridges of the dual function. Third, when updating the multipliers using subgradient directions with the intent to maximize the dual function, in the next iteration, a dual value may become lower than in the previous iteration. So subgradients are generally not ascending directions. Also, subgradients may be almost perpendicular to directions toward the optimal lambda. What does it lead to? That leads to the drastic changes in subgradient directions, which leads to zigzagging of multipliers and slow convergence as the result. Here, I will mention the key stages in the development of Lagrangian relaxation and non-smooth optimization. To guarantee convergence of multipliers, in 1969, Pollack's formula was developed. It was proved that multipliers converge to the optimal multipliers geometrically. The optimal dual value, which is used to set step sizes, however, is not known. Nevertheless, the step sizing formula gave rise to numerous applications to solve MLP problems by using Lagrangian relaxation. In 1999, another method, surrogate subgradient method, was developed to reduce the computational effort by solving one or few subproblems in order to update multipliers instead of solving all the subproblems. That leads to reduction of computational effort, and that also alleviates zigzagging of multipliers. It was also proved that there is a geometric convergence. However, within both of those methods, optimal dual value is needed, which, however, is not known. This is the key slide of this presentation. This is on the development of the novel surrogate level-based Lagrangian relaxation. The main question that I intend to answer is how to get closer to achieving geometric convergence, but without knowing the optimal dual value. We know from the previous slide is that if step size satisfies the Pollack's formula, then multipliers converge to the optimal multipliers. On the other hand, it can be inferred that if multipliers diverge, then it's only possible when step sizes are too large. How does it help us? We still do not know the optimal multipliers. Here's the idea. If during n iterations, we can detect that multipliers do not converge any value, including the optimal dual value, that would also be only possible when the step sizes are too large. So there exists an overestimate of the optimal value, and step size equals to this quantity. So the procedure is to solve the auxiliary problem to detect divergence, then to infer the level value Q, the overestimate of the optimal dual value. And since we know step sizing formula is too large, we reduce the step sizing formula in the future iterations. This simple idea really gets the job done. For testing, I have chosen the generalized assignment problem. The problem is to assign a set of parts or jobs to a set of machines, and to minimize the assignment cost, the total assignment cost. The problem is subject to machine capacity constraints, which say that the total time of assigned jobs on a given machine should not exceed the total available time on a given machine. Assignment constraints require that a job is assigned to only one machine. In case study 1, I considered instance type D, which is considered to be one of the more difficult ones. And the size of the problem is 10 machines and 400 jobs. Here I demonstrated how the dual value increases within the new method, and as well as within two more competing methods. What I found out is that the new method leads to faster convergence. Also, within the new method, no hyperparameter adjustment was necessary. What was necessary is to solve this auxiliary problem to obtain the overestimate of the optimal dual value to set step sizes. Those overestimates, by the way, can be used as upper bound to quantify the quality of the upper bound, also shown in this figure. This comes at a cost. However, the extra cost to solve the auxiliary problem is less than 1/5 of a second. For the case study 2, I consider larger instance with 20 machines and 1,600 jobs. What I have found out is that the method is robust against the choice of initial step sizes. The method is also fast. For comparison, standard branch and cut method, the same method that I use to solve subproblems, when it's used without decomposition, it is slower by at least 2 orders of magnitude. And the feasible cost is not as good. For this problem, the auxiliary time is roughly 2.5% of the total time on average, which is not too much. Then for the case study 2b, here I consider 2 more instances with 40 machines and 80 machines. What I found out is the method is scalable and it's also competitive. I compared the method with the best method that had been available. What I found out is that for the instance with 20 machines, the results are comparable. For the larger instances, the method that I had developed was in fact able to find optimal solutions. And it's much faster than previous methods. For the largest instance, the total time was about 1/3, 1 hour versus 3 hours. In conclusion, the major breakthrough is that the novel method efficiently exploits the geometric convergence potential offered by the Pollack's formula with little or negligible overhead required to solve the auxiliary problem. What I found out is that the method is robust against initialization, cautiously optimistic that we're moving toward hyperparameter-free optimization to ensure convergence in the dual space as well as in the primal space to obtain good feasible solutions. A note on nonlinear problems. The method, at least in a dual space, does not require linearity or separability to establish convergence. Therefore, there is a potential to solve a broader class of mixed integer nonlinear programming problems. For the 2 largest instances that I have tested, the method obtained the optimal solution. In general, the optimality cannot be proved, so the method is near optimal and computationally efficient. The new method lays foundation for microgrid coordination, self-optimization of factories, supply chains, DNN training, and beyond. Thank you. I would like to take a few questions. Stay safe.